Hello and welcome to the session. Here we are going to say it in a formal fashion. Spectroscopy, that's the study of interaction of light with matter. So we see the different colors of various objects around us. That is because of the reason that when white light, which is made up of 7 colors, it falls on a given substance. So the matter, the material, it absorbs some of the wavelengths and reflect other wavelengths. So in this manner, based upon what wavelengths are absorbed and what other wavelengths are reflected by that object, so the colors of those objects are going to appear. Different substances, they can absorb different wavelengths of light, and this information could be used to get various useful pieces of information about that substance. So now we are going to take a look at some basic information here. So the electromagnetic radiation that is made up of photons, and the photons has two vectors. It has a magnetic field vector and an electric field vector. Diagrammatically, it is represented here. Now, some basic terminology. Frequency is described as the number of times the field is oscillating in a given period of time. Generally, the period of time is a second. So in 1 second, how many oscillations occur? That is called as the frequency. Frequency is expressed in terms of hertz. 1 hertz is 1 cycle per second. Wavelength is the distance between two points on a wave which are present in the same phase. So that is called as the wavelength of that wave. And amplitude, that refers to the maximum degree of oscillation from the point of equilibrium or from the midpoint. Another way to describe the waves is in terms of wave number, and wave number is given by this expression that it is the reciprocal of the wavelength. Now here you can see a diagrammatic representation of a wave. So the distance between 2 points on the wave present within the same phase, that is called as the wavelength. And the maximum displacement from the midpoint, that is called as the amplitude. The wavelength and frequency, they are related by this expression where C equals wave number times the wavelength. So this expression could be described in terms of energy as well, that the energy would be equal to hc over lambda, where h is the Planck's constant, c is the speed of light, and lambda is the wavelength of that light. This figure represents the wavelength and energy of different types of electromagnetic radiation. So on the left side, you can see the radiation with the highest energy, which are the gamma rays. And as we move towards the right side, we see the light or the electromagnetic radiation with with greater wavelength and smaller energy. And here, this is the visible spectrum. So all of these different colors which we see, they fall into this small region of the wavelength. Rest of the other wavelengths of light are invisible to us. Now, this is representing the wavelength of the visible light. So, corresponding to red having the highest wavelength and the violet having the least wavelength. So, this is the same information provided in terms of a table. So, the fundamental principle of spectroscopy is the measurement of the spectrum of a substance. That is, what radiation a given substance is absorbing or emitting. A spectrometer is an instrument which is used to measure the spectrum of a given substance. One of the mechanism of spectroscopy is called as absorption spectroscopy. Here, we monitor the absorbance of a given specimen. Many a times when we deal with biological specimen, the solutions are the specimens. So we prepare the solution of a given substance and then we can monitor the spectrum of that substance. For example, UV absorption spectroscopy measures the absorption spectrum of a substance within the UV range. Visible spectroscopy measures the absorption of a substance within the visible range of wavelengths of light. Many of the spectrophotometers, they contain both the UV and the visible absorption measurement function in them. So they're called as UV visible absorption spectrometers. This is one of the UV visible spectrometers which is represented here. The other type is the emission spectroscopy. When a certain type of radiation is incident onto a given material, onto a given specimen, then the specimen itself, it emits radiation. This phenomenon is called as emission. So the measurement of emission is called as emission spectroscopy. For example, mass spectroscopy. So now we come to two important laws referring to spectroscopy. So Beer's law states that when light passes through a given solution, the amount of light being absorbed by that solution is directly proportional to its concentration. The amount of light absorbed is also proportional to the path length. Path length refers to the distance which light is traveling through that solution. Generally, the path length is fixed at 1 centimeter. So here you can see in this formula that A, which is the absorbance of a given solution, equals epsilon CL, where epsilon is a constant and this is called as the extinction coefficient. C is the concentration of the given solution and L is the path length. Generally, the path length is standardized at 1 centimeter. So, epsilon is also a constant. So, the absorbance of a given solution is directly proportional to the concentration of that solution. If we rearrange the equation, so it gives epsilon equals A over CL. Now, if the concentration is 1 molar and the path length is 1 centimeter, so the extinction coefficient would be equal to absorbance. So the extinction coefficient here, called as the molar extinction coefficient, could be described as the absorbance of a solution of 1 molar concentration when the light passes through a path of 1 centimeter. In this way, the extinction coefficient could be experimentally determined. Another important implication of the Beer's law is that we can experimentally determine the absorbance. The extinction coefficient of most of the substances are already known. The path length is also fixed. So therefore, if we have a solution of unknown concentration, then we can experimentally determine the absorbance of that solution and can therefore calculate the concentration of that solution. So this is one important implication which is routinely used, that we can calculate the concentration of a given solution by monitoring its absorbance. So the UV is ranging from 10 nanometers to 400 nanometers wavelength, and the visible follows it. So there are other regions as well, which are near UV and far UV, and their wavelengths are given here. The substance which is important for imparting the color is called as the chromophore. Chromophore is actually the part of the molecule or a group of the molecule which is responsible for absorption of a particular wavelength of light, and under visible conditions is important for producing color. So therefore, such substances are called as the chromophores. So these groups given below are examples of different types of chromophores. Every different type of a chromophore has a characteristic pattern of absorbance. For example, alkenes, they show absorbance around 200 nanometer, whereas carbonyls, they show characteristic pattern of absorbance within this region. Anoxochrome is a substance which is, when attached to a chromophore, it modifies the ability of that chromophore to absorb light. For example, benzene shows maximum absorbance at 255 nanometer. But when benzene is modified by attaching a hydroxyl group here, it turns into phenol. So this hydroxyl group attached to benzene alters the absorbance characteristics of this benzene molecule, and the absorption maximum is at 270 nanometer, as opposed to benzene, which shows maximum absorbance at 255 nanometer. This molecule shown here is aniline. It contains an amino group attached to it. So it further modifies the absorbance pattern of benzene, and now the maximum absorbance is at 280 nanometer. The wavelength at which a given substance shows maximum absorbance is called as the absorption maxima. So here you can see that in case of benzene, maximum absorbance was at 255 nanometer, but the addition of these functional group has modified the pattern of absorbance. So hydroxyl group and amino group are examples of oxochromes which have modified the absorption pattern of this chromophore. The chromophore here are the double bonds present between carbon atoms. Spectroscopy has various important applications. It could be used for qualitative as well as quantitative analysis. Now, different types of chromophores and they have a characteristic pattern of absorbance. So, this can be used to determine the nature of the functional groups which are present in a given substance. So, every given functional group has a unique pattern of absorbance. So, by looking at the characteristic absorbance of a given substance, we can find out what type of functional groups or what type of aromatic compounds are present in a given substance. This could also be used to find out the molar concentration of a solute. We have looked at it previously by using the Beer's law. So we can, by using the extinction coefficient and experimentally determining the absorbance, we can calculate the concentration of a given substance. Spectroscopy could also be used for the detection of impurities. We have seen previously that every given functional group has a characteristic pattern of absorbance. So if a unique pattern of absorbance for a particular type of functional group is found, that means that particular functional group is present. But if we have different pattern of absorbance, that indicates that other functional groups may also be present in the given substance. So the sample may be containing impurities in it. Another important implication is that different isomers they have of a substance have different pattern of absorbance. So by having a spectrum of absorbance, we can find out the nature of various isomers present in a given substance.